in the Arctic.
После проигрыша или так? Добрый день, уважаемые коллеги.
Hello, dear colleagues. We are starting the second day of our Northern Sustainable Development Forum. And today we're having a roundtable, Permafrost monitoring and infrastructure stability in the Arctic. I would like to greet our participants who are in online, and we're having this online and offline combined round table. We have here colleagues at the venue. Here we have Yuri Borisovich Skechkov from the Institute of Permafrost, Melnikov Institute of Permafrost. We have Oleg Trigubov, head of Laboratory of Regional Geoecology and Geocryology of Chukotka Department of Northeast Interdisciplinary Scientific Research Institute of the Far Eastern branch of RAS, and the Deputy Director of Melnikov Permafrost Institute, Alexander Fedorov, co-moderator, and I am moderator. My name is Mikhail Zhelezniak. I am the Director of Melnikov Permafrost Institute. We also have here our colleague that we've been working with for quite a long time, Iohana Go, Professor, International Arctic Research Center, University of Alaska. We also have Alexander Fedorov from the Melnikov Permafrost Institute, and Stepan Varlamov, the leading research scientist of Melnikov Permafrost Institute Laboratory. Dear colleagues, I will now announce the time frames. We have 15 minutes per presentation. If we have time for questions within our time limits, then we will have questions. If you don't have time for questions, we proceed to the next speaker after some comments from the moderator. So, dear colleagues, let's start our work. I would like to greet you once again, all our online colleagues. Hello there. So the first presentation, it's monitoring of Cryolithozone in the Arctic.
Коллеги, включите, пожалуйста, презентацию. Значит, это комплексный доклад.
This is quite an interdisciplinary presentation by a group, a team of the Melnikov Permafrost Institute.
Так, мониторинг криолитозоны в Арктике Российской Федерации.
This is dedicated to permafrost monitoring in the Russian Arctic.
То, что есть
And I will mention what trends we have, what work we do on monitoring of our Russian permafrost.
Уважаемые организаторы, не переключается слайд.
In modern distribution of permafrost, we know that the entire area occupies around 30% of the land surface, and about 65% is Russia, and almost the entire territory of the Sakha Republic. And the peculiarity of Arctic territories are very low temperatures of air and the presence of permafrost and ground ice. In the northern regions, permafrost is rock-forming material, and the ground is very peculiar due to dynamics of permafrost. This is a crucial factor that defines the geodynamics of northern grounds.
Вот чего-то не получается у нас. Одну минуту, извините, сейчас мы наладим. Ну, здесь показано, мы
Here
говорим
you see
о мерзлоте, мы говорим о
the
климате.
permafrost climate, and these are
Изменения
characteristics of behavior of temperatures, of near-ground temperatures in Russia
в целом по земному.
and globally.
Говоря об изменении климата,
If we talk about climate change,
Земли,
of course it embraces the entire territory of the planet, and here this is the data of Mr. Skechkov, the data on climatic parameters of alteration of the near-ground air temperatures. The largest changes, the highest and the largest changes occurred in central Yakutia, as you can see, and in some Arctic districts.
Ниже слайде показано, как изменяется.
And below, this is the changes of precipitation. And you can see that in the Arctic zone, precipitation is getting less. So what is the reaction of permafrost to climate change?
Реакция криолитозона.
Of course, the reaction of permafrost.
Уважаемые коллеги, включите, пожалуйста, нормальную презентацию. Ну, реакция криолитозона на
The reaction of permafrost to climate change
различные тенденции.
can be different and has different trends. Although it is observed in the majority of territories, and there is changes in the depth of active layer, changes in temperature. You can see the active layer thickness in some parts of eastern Siberia, in Arctic districts, and in southern districts as well. In the majority of the territory, the depths of seasonal thawing can fluctuate between years and less trends of temperature change.
Ну, подключите сейчас слайды. Сейчас, одну минуту, техническая неполадка, потому что говорить о... Так. Вот на слайде представлена реакция криолитозона.
And this is the reaction of cryolithozone, how the temperature of grounds changes in different landscapes in central part of the Sakha Republic, in southern districts, and the lower curve shows you the fluctuations of temperature in Arctic district. Also temperatures at these shown depths. And we can see a trend, different trends. The highest trends of change in Yakutia and eastern Siberia are observed in mountainous and pre-mountainous areas. Cryogenic processes that modify surface and connected to climate change also change the geological conditions. First of all, it damages roads, because roads are deformed, among other things, due to permafrost changes. Again, we have here deformation of gas mains, electric power lines, structures and buildings. No doubt, cryolithozone is a very special environment of biological and geological conditions. And the provision, ensuring of well-being of engineering structures in the north, it is not possible without taking into account the factor of permafrost. In 2020, the Ministry of Development of Far East, together with permafrost scientists, studied the trends of permafrost behavior, and they presented this huge work where they have forecasted and analyzed the current state and what should a system of monitoring should be. And we assessed the price of all the buildings and structures within municipal districts of Arctic In Russia, it is estimated at 9.6 trillion rubles, and 1.1 trillion is residential properties. And the damage to residential properties by 2050, including if we consider all those scenarios, it is estimated at 5 to 7 trillion rubles. And the damage to only residential buildings that we are having now, it's about 770 billion rubles. Creating this interagency system of state monitoring is crucial, because we should monitor permafrost and provide very professional expert recommendations. And it is estimated at 12 billion rubles. These are some estimations on deformation of buildings in the Arctic. And in order to have an appropriate approach to monitoring and analyzing, processing the entire data, we need to create a structure of administering this monitoring system. And we think that this system, all the permafrost researchers think, actually, there were over 100 researchers, I think it should be one separate agency, public agency or public ministry. Why? Because the system of monitoring should embrace the background monitoring, technical monitoring, baseline monitoring. That's why the coordinating body should be present. This is again the same. So what is the organization of Interagency Analytical Center? All the data collected should be accumulated in one center, and we should create these federal analytical centers, or maybe regional analytical centers. So what are the immediate actions needed to address permafrost impacts of climate warming? First, what we suggest now to do in Russia, the system of Roshydromet, it is not complete, and it can't be viewed and only can be viewed as part of this universal permafrost monitoring system. It will be just a part of it. It won't help us to the extent that we want to. We should use this capacity we have in the Republic, and the program of research that are undertaken now, and we have the possibility to create a universal, a comprehensive system, as we suggested in our project, in Yakutia, uniting very different geomorphological permafrost conditions that we have here inside the Republic. I think we can complete it by 2023, but we need some funding. The second point, what do we immediately need to do is to establish an international experimental test center in Yakutia for road research. Because we are planning to build a lot of roads, and Yakutia is a perfect place for such a test center. Even we have already made the first steps. Rosavtodor of Yakutia. And the third one, Yakutia initiated and adopted the law on rational use and protection of permafrost. It is now reviewed at the federal level, and I think it should become federal as well, because it seems to be functioning. Next thing, we need to find ways to interact and cooperate with research organizations and companies that operate in the licensed areas, because we need to get some fresh and very true data that we can get from companies. And the fifth thing is that it is important to improve regulatory documents, including engineering, site investigation, and permafrost modeling. Thank you for your attention. Dear colleagues, the time limit, unfortunately, is depleted, so maybe we can ask your questions and share comments after the session. So I just gave you a brief overview of a system that we want to establish and what is the general status of these problems in Russia and what approaches should we use to study them. So the next report, I will give the floor to Mikhail Grigoriev.
Good morning, dear colleagues.
Ждем доклад, когда будет презентация. Название доклада – это динамика трансформации многолетней
We're going to be talking about the dynamics of transformation of permafronts in the delta, shelf, and coastal areas of the Russian Arctic.
Сейчас название зачитал модератор. Этот доклад был подготовлен.
This report has been prepared by the Permafrost Institute
коллегами из АНИИ, с нашими коллегами из
with our colleagues from the
Гельгон-центра
Arctic and Antarctic Institute from St. Petersburg, as
такой
well
центр
as
полярных и морских исследований.
Helmholtz Center of Polar and Sea Research from Germany.
Вы видели, такая у нас картинка довольно
And
популярная.
you
Понятно,
know
что
this map, which is quite actual for the moment. This is all the coastal area of Arctic seas, and
как бы вечная мерзлота на
in all these seas there is permafrost in large areas,
такое явление, как
and
мерзлота.
there is such a
Знают, что это
feature as an underwater permafrost. Not many people know that the permafrost occupies quite large areas under the sea and under lakes and sea lagoons and so on. There are many different varieties of underwater permafrost, which was mostly formed in late Pleistocene, when the sea was leaving the
то, что сейчас
coastal areas for 100 kilometers and more, and
распространение многолетних мерзлых пород.
the current permafrost underwater is where the original permafrost used to be during this time. And this is how our colleagues from the United States show the spread of underwater permafrost, and this is the arrow that where you can see where it is in the Russian Arctic and partially in Alaska. Permafrost here is shown on this map, the one which has been researched, and there's basically some estimations there as well. Mostly estimations, actually, because there's not much data on undersea permafrost. At present, in the recent 5,000 years or so, when the sea has stabilized, sea levels have more or less stabilized, undersea permafrost is like this, as you can see on this slide. The coast is regressing at about maybe 10 meters or so, and for thousands of years, an underwater permafrost forms, which has been continental previously and now becomes undersea one. And this is how it looks like. And this is the organization of tractor drilling trains. This is quite difficult work. And these are all the known drilling profiles in the seas of Eastern Siberia, and there are a number of maps and models of the spread of underwater permafrost in the Laptev Sea and the Eastern Siberian Sea, and they mostly show that the permafrost exists up to the continent itself, continental shelf. And however, these models, they are based on the calculations of heat waves and heat streams, but there is no real specific data on the shelf and on the real spread of permafrost. That's why we need to be slightly wary of these models. There are two types of underwater permafrost. It's the relic and newly formed permafrost. So the newly formed ones are basically in the river deltas and in shallow areas where the ice is being deposited underwater, and it's not very thick. And here you can see the borders of permafrost in different conditions. It exists in some places. For example, in the Skechkov Strait, it doesn't exist. And it mostly exists where the coast is regressing quite fast.
Ну вот не получается. Что-то вот неправильные какие-то пчелы тут. Вот, да? Ну вот, значит,
And here you can see the drilling profiles of fast, rapidly regressing coasts. And you can see that the permafrost there is up to 1 to several tens of meters deep. And these are the drilling profiles in the eastern part of the Laptev Sea, in the western part of the Laptev Sea. And there's quite a lot of data on its composition. And I want to draw your attention to the temperature. The temperature is quite warm, actually. It's up to -1 to -2 degrees. That is basically the undersea permafrost. It's not very stable because its temperature is near 0 degrees. And if these underground deposits become slightly salted, then basically this permafrost is going to be not really a permafrost, but it will be like just rocks, soils. And here you can see these profiles where the temperatures are near 0 degrees, and the further we go from the coast, the nearer the temperature is to 0 degrees. And it seems that this permafrost will basically disappear the further we go from the sea. But then again, it does exist in quite a large distance away from the coast, up to like several tens of kilometers. And this is the data of monitoring for 30 or almost 40 years in the Laptev Sea. And you can see that the coast is regressing, and the permafrost in red is how it looks like 30 years after, in 2014. So this is the speed of destruction of this undersea permafrost, and it reaches up to 30 and more centimeters a year. And this is the average speed of regression of permafrost. It's about 5 to 8 centimeters a year, and these are the average degrees of its slope. And this is how this sloping looks like, and they're very different in different coasts, depending on the speed of regression of the coast soils. And we have very steep slopes in some areas. And in river deltas, under river deltas, permafrost has been studied there, and it does exist there, and it also looks different. And in general, it exists where the depth of the delta is up to 4-5 meters, and it's almost everywhere in such places we have underwater permafrost, with the exception of the deeper areas. And we often find gas, methane, when we are drilling these holes. And we're seeing that this is due to the local organic materials, and there is quite a complex permafrost under lagoons, which is sporadic actually and not continuous. And there's quite a large stream of gas. You can see it here. It's oversaturated. The ice there is oversaturated with gas, and there are these bubbles of methane there.
Алло. Коллеги, пропала презентация. Да нет, ничего не нажал. Алло. Можно включить презентацию? Ну, как-то, конечно, без картинок. Не очень понятно, не очень... Ну, давайте я очень коротко скажу о...
So I will talk briefly
о береговой мерзлоте.
About the coastal permafrost. We've been talking about underwater permafrost, but the coastal permafrost, there are quite many different varieties of this coastal permafrost. Our coasts are very ice heavy, and they are very complex, and the ice is up to maybe 90% of the coasts. And this is widely spread.
Организаторы, вы меня слышите? Не идет презентация у нас. Уже давно.
In the Laptev Sea, in the East Siberian Sea, and in Chukotka, Alaska, and the Beaufort Sea, there are quite a lot of icy coasts, and we have researched them in quite a lot of detail. And there are over 50 key sites where we see the regular erosion of coasts due to thermal abrasion mostly, and it's up to 25 meters a year, the average regression of coasts in the seas of eastern Siberia. 1.18 is the icy coast, and the others are different coasts. So these are our key points, key sites.
Как-то вот техническая часть у нас подкачала. Так, уважаемые коллеги, презентация плохо идет, давайте что-то делать с ней. Ну, давайте я сейчас буду заканчивать, тогда здесь просто... Пошло. Ну, да, вот видите, у тебя получилось. Да. Дальше тогда. Ага. Один раз коротко нажала. Ну, да, да. Ну, вот, давайте я уже... Ну, тут основные принципы были, как мы считаем.
We have seen the main principles of how we get the data and the volume of data that we get from the sites. And this also includes organic carbon. And this is quite important at the moment because there are quite a lot of projects we have connected with climate change and this allows us to see how much of carbon and methane is released when the permafrost melts. And this is the example at the Mostach Island, which will soon disappear, basically right before our eyes. And some conclusions here is that at present we lose about 10 to 11 square kilometers of land a year in these two seas of Yakutia. And this land the amount of land we lose, and lots of materials, including about 4 million tons of organic carbon, are released due to this loss into the seas. And thank you for your attention. And I also want to say, in conclusion, that the monitoring that we're doing in the Arctic, in the coastal areas, and when we monitor the underwater permafrost, it's very important for the people who live there, especially the dynamics of coastal regression, because there is infrastructure there. And the monitoring of this process in the Arctic is very important, and we are continuing with his presentation. Dear colleagues, we are continuing our roundtable, and now I give the floor to Yuri Skechkov, Senior Research Scientist of Melnikov Permafrost Institute. And we are going to be talking about the current climate changes in Yakutia. Good afternoon, dear colleagues and participants of the forum. And you can see the topic of my speech today. And before we start talking about what's going on with climate in Yakutia, I'd like to tell a few words about the background of these changes. For example, this is our planet. And from the end of the 19th century, when there have been many meteorological observations and stations that were monitoring air temperatures, we can see such changes. And from the beginning of the 20th century, there is a growth in average air temperatures with a peak in the 30s and 40s. And this is called the warming of the Arctic. And then in the 1940s, 1950s, there has been a small drop in temperatures. And then starting from 1970s and up to the modern times, we can see the rapid growth of these temperatures. And in general sense, this global warming from the end of the 19th century up to now, and in a more specific manner, well, this is considered to be a global warming. And you have already seen this slide. And if the temperature has been mostly without much changes globally, but here in Yakutia, the changes have been more rapid, sharper, and they are growing actually quite. The air temperature doesn't grow everywhere equally, and in some places it grows higher, more rapidly, and in some places it is slower, and it grows more rapidly. It rises more rapidly in northern latitudes. And because Russia is a northern country, we can see the trends from 1976, and the highest trends are in the Arctic of Eurasia, and you can see in Yakutia.
Вы слышите меня? Алло. Презентации нет, мы не видим картинок. Все графики, схемы, которые прошли, мы не видим их.
Это ваши проблемы.
Нет, это не наши проблемы.
Так, техническая
служба. Сейчас застыло все, да.
Одну минуту. Уважаемые коллеги, вот
So in Yakutia, we have done an analysis of the growth of the mean air temperature, annual air temperature, and we came to the conclusion that this growth can be seen in all meteorological stations of Yakutia. And on the basis of these trends, we have seen the growth, and it is actually quite telling. First of all, the trends, the highest trends, have been seen in 12 meteor stations, 0.6 to 0.8 degrees in 10 years. And the growth of average temperature were 2.3 to 4.2 degrees in the last 54 years. And the smallest trends are in 4 meteor stations, and they only increase, temperature increase only by about 1.5 degrees. So we can in general say that the temperature in the Republic has increased by about 2 degrees, as we can see on this map. Yakutsk has the highest growth, 4.3, and it's possible that this is the influence of the city in the last 20 years, because we haven't seen such a rapid growth before in this area. And in the north, you can see the temperature rose by about 3 and more degrees. As for the annual precipitation, there are both positive and negative changes. Of the positive ones, 7 are statistically significant. And in 3 stations, they showed negative trends. Other meteorological stations did not see any changes. So it's basically, as you can see on this map, there's zero dynamic seen in black here on this map. Once again, I want to repeat what Mikhail Grigoriev said, that in the Arctic seas, with the exception of Chersky, there is the drop in the amount of precipitation. However, in the south, there is a significant growth in precipitation. Well, it's quite obvious because it's a different region.
Все ясно. Так, перескакивай через один. Ну вот сейчас вот немножко поговорим о...
We are going to talk a little bit about Yakutsk, the city of Yakutsk, because there is the longest uninterrupted data collection from 1893. And we can see that the changes in air temperature are consistent with the mean global temperatures and Russian temperatures. And we can see that there is some growth in the 40s, and then there is some drop. And then beginning in the mid-1970s, there is a rapid growth of temperatures. And this slide shows the data from the last 54 years. We can see that if in the 60s, 70s, and 80s, the mean annual temperatures have been from -11 to -12 degrees, then subsequently, due to the rise in these temperatures in the last decade, we can see that there are very high temperatures. And in the last year, it was very anomalous, both globally and in Russia and Yakutia, and the average temperature was -5.9 degrees. This is the highest temperature for all the period of not only observations, but also the whole period of existence of the city. And these are the record-breaking years, as you can see on this slide. So between the first and second place, there is a 0.8 degree difference. It's like a huge difference. If in the previous years, the temperature change was only 0.1 or something like that, but now it's like 0.8. And this slide shows the precipitation in Yakutia. And as you have seen on the map, there's basically no changes. So there's no significant changes in the trend there. And the norms of principal meteorological data here, indicators here, which are used in many different areas of our activities. And the previous norms that have been calculated from 1961 to 1990, they are outdated now. And this period has been proposed by the International Meteorological Organization and our Rosgidromet. And starting from next year, we're going to have new norms, which will be more real and will correspond more to present times. And here you can see how the temperature changed in 30 years. So in winter, the difference is up to 4 degrees. And in summer months, there is not such a significant change. But starting next year, in our publications, we're going to be using these new norms. For atmospheric precipitation, you can see that there are basically no changes here in central Yakutia and in the city of Yakutsk. There is not much precipitation, and this means that we have a steppe climate here, basically a semi-desert. And the last year was phenomenal in both globally, where the mean air temperatures have increased quite a lot, and in many cities of Europe, Russia, and other countries, and in Yakutia, we have seen high positive anomalies. And you will see the map now, which was published by Hydrometeor Center of Russia. And we can see how much was the difference from mean annual air temperatures. And in Yakutia, it was from 5 to 6 degree difference. And we'll see how it changed in several centers. And this is the 10 record-breaking places where the temperatures have changed. And we can see that the norms of 1961, 1990, which I mentioned before, are outdated now. And the difference in Tixi, Saskalach, and Alenyok is from 5 to almost 6.6 degrees from previous mean temperatures. And in Yakutsk, the norms were exceeded by 4.1 degrees. This year, the summer was also anomalous throughout the whole of Russia. In Yakutia, this anomaly amounted to 2-3 degrees. You can see this nucleus there, colored red here, which was spread over most of Yakutia. What does this say? Well, there have been quite a lot of forest fires this summer during this dry period from May to June, when the fire started, when we only had 12 millimeters of precipitation in Yakutsk instead of 18, and only 2 millimeters instead of 30 in June.
высокой температуры,
And in addition to high temperatures,
кроме малого количества осадков,
I
была
mean,
очень высокая
instead
температура.
of low precipitation, there has been very high temperatures in May and June. In July and August,
Вошло в норму.
everything was normal as used to be. Thank you.
Спасибо, Юрий Борисович.
Thank you, Yuri
Мы с вами
Skechkov.
вот немножко окунулись.
And we have heard a little bit about the climate atmosphere in our republic. Dear colleagues, the next speaker is Oleg Tribgubov, head of the Laboratory of Regional Geoecology and Geocryology of Chukotka Department, Northeast Interdisciplinary Scientific Research Institute of the Russian Academy of Sciences.
Значит, новое направление климатического мониторинга деятельного слоя. Вот здесь интересное название.
So this is the new directions of climatic monitoring of active layer in Anadyr lowland in the Chukotka.
Тема моего сообщения,
So the
так
topic
я его
of
обозначил.
my, I better prefer to call it message, was worded already. So let's talk about it.
Прежде всего,
First of all,
хотелось бы сказать о том, что мониторинг
monitoring has
вошел
become
во все сферы нашей
an
жизни.
everyday activity for
Можно
us,
сказать, даже так стал уже
and it
глаголом
even
русского языка. Что
became a part of Russian language, to monitor. We can monitor anything now.
Тем не менее, термин не так уж давно
But
и появился.
the term has been borrowed not very long ago. It happened
Его появление связано
in the middle of 20th century.
хозяйственной деятельности человека,
It was used to assess the economic activities of human
истощение природных ресурсов.
and its impacts on environments, including pollution.
Актуально наблюдать эти
So it
процессы,
became relevant to monitor these processes and try to control them,
загрязнений и сохранить
try to cut the pollution and save resources. Back then in the USSR,
считают Израиля,
the
который
man who started it,
который сформулировал
the member of Academy of Sciences who formulated the key concepts of monitoring, we can see it here. It was Mr. U.A. Israel. So we use this concept to develop our systems of monitoring. And that's why we also have some long-standing problems inherent to the system. The concept was first introduced in 1978 and then in 1984. The difference of this concept between these two concepts is the addition of feedbacks. You can see it on the chart. The black arrows now go from assessment of factual status and from assessment of forecasted status, and even from administration, they all go to observation. So the planned monitoring to assess negative impacts of economic activities. So the one who wants these data is actually the company, economic entity, and that's why they can manipulate the results if they don't like the data. And that is why, if the company has a internal monitoring, sometimes this monitoring gives you exactly the data you want as a company. And the distributed scheme that you can see on the right, it's actually a very simplified one, and monitoring and the content of monitoring depends on scale, on the object, on the target. We heard partially a report about monitoring. What targets of monitoring are, this is also crucial. Gray-colored, these are the subsystems, and among these ones, environmental, sanitary, and there is also climatic monitoring. And this is what I would like to develop on. First of all, the concept of climatic monitoring has been changing. I've looked at many definitions of the term. Initially, climatic monitoring was a synonym of to monitor the climate, but with accumulation of data by the end of the last century, we had changed our views. Climatic monitoring studies not only how climate changes and what happens in the atmosphere, but everything that happens in the interlinked system. All the objects of climatic monitoring can be different. And the last definition that I find the most appropriate to what are we doing, in fact, it's a systematized observation and analysis of status of components of environment with aim to forecast climate change and assess impacts of how these changes impact the environment and life support systems of human. So it includes biogenic, abiogenic, and other systems. But in fact, it considers the direct impact of climate on these systems. So the methods should be same in different regions. The observations should be continuous and non-stop. And these methods should not change to comfort any desires. They can be expanded, but they cannot be shrunk. So this is our approach. This is what we do, climate monitoring of cryolithozone. Has to do with the upper layer of permafrost, which sometimes called the annual temperature turnover layer. It includes seasonally thawing layers, soils, grounds, above permafrost and intra-permafrost waters. It's a very complex system. And it's very hard to monitor it using only one approach. And again, we have to add cryogenic processes in the equation. So this is the monitoring in Anadyr lowland. It started in 1935, since the Anadyr permafrost station was established, but systemic modern climatic observations started only 25 years ago, when we established CALM stations. It's a very well-known international project. It is aimed at monitoring and observation of changes of seasonally thawing layer, aimed to assess the climate impacts. And today we are talking about the possibility to forecast climate change in future. I will mention that later. I won't go into details to describe the methods, but you have it in my presentation, and many of you colleagues know how it works. And via this program, we acquired a lot of automated equipment, using which we monitor temperature. We have 3 sites in Anadyr lowlands. In 94, 96 to 2010, they were established, and we monitor thermokarst, thermoabrasion annually, thermal heaving. We have 3 holes where we monitor temperatures. One of them is located in the city of Anadyr. Of course, it's not a baseline monitoring. And the results, the upper chart shows the curves, how the depth of seasonal thawing changes. The curves are very beautiful, and it gives you an impression that you can work with it, to process them and to look for those factors that influence the depth of seasonal thawing. And below we have the seasonal temperature fluctuations, mean annuals in Anadyr station, although they are quite calm, quite flat, because we combine them in one diagram. The fluctuation, the variability of temperatures compared to the thawing layer, the temperatures, we have it's comparable. And over 25 years of monitoring, we've been assessing all the aspects of changes, climate, permafrost, and these are the two works published in 2019 and 2020. And a very quick check that can give you a fast result has to do with mean annual temperature of air, of course. But there is no very strict direct connection. It varies between different landscapes. There is a more important connection between these temperatures of between different years. At this graph,
который мы смотрели, конечно,
that previous graph, we see the interannual fluctuations with different periods. These periods, we were not the first ones to find it out. For another lowlands, we have this short periods, 2-3 years, because the amplitude and the period changes, and then we have fluctuations between 8 to 11 years. We tried to systematize these graphs by Fourier series. We had about 9 of these, and their informational value, except for 2, is not very high. That is why we used kinematic approach. We tried to single out these series and tried to decompose them into elements from where we could gain some physical meaning. The upper one is the mathematical decomposition, and you can see the sinusoids and the remains. We can also see the coefficient of approximation accuracy here, which is quite high. But we knew before that the amplitudes will be changing, the periods will be changing. And in the lower graphs, we just very slightly corrected this unharmonical sinusoid curve. And this trend of growth of thawing depth turned almost into a flat line. So the coefficient is very indicative for us, and it becomes quite clear. Another conclusion from this processing is that we might forecast the thawing depth for at least short term, which will be equal to the historical observations. Because it's an ascending branch, it might, in fact, be a section of some other curve of longer fluctuations, maybe like a century long or less. But nature is always cyclical. But every cycle is different. Despite such approach, we still want to single out those factors that influence the thawing depth and all those links that exist. That's where we got the idea to monitor and observe other parameters as well that would be linked to climate change and to the thawing depths. The first that we thought of is to monitor the seasonal ice content. The higher ice content at the beginning of thawing, the less is the thawing speed rate. And where we have ice-containing horizons, the speed of thawing will be not even over this warm period of year. It was obvious for us, the first one. And after we started these observations in 2018, we started working with the data. We found out that not less important is to monitor humidity of active layer soils and to monitor actually the entire suprapermafrost water horizon and its water content and its surplus or deficit of water. It will be influencing the intensivity, the rate of seasonal thawing, but at the same time it will show us this negative impact of climate change. For example, aridization or more humid conditions, humid conditions. So these were our ideas, and in 2020 we started these experiments. You have 1 minute. So we've installed sensors, and except for ice content, we want to monitor the entire suprapermafrost horizon. Here you can see the technology of how we sample core, how we log these layers, and we are trying to also use resistivity method to count ice content. We have both seasonal and perennial grab sampling channels. Here we are installing the level measures in thermokarst lakes in lowlands. They are connected hydraulically with suprapermafrost water-bearing horizons, aquifers. And the conclusions will maybe available later because it's just very short term. But at least we try to assess the reserves of these ice contents for certain landscapes. For example, here you can see the millimeters of water layer. It's the reserves of water in PT lands, lowlands. So these water reserves are comparable to summer precipitation, liquid precipitation. So you can imagine how important for everything, for active layer, for ecosystem, for freshwater ecosystem, how important the seasonally thawing layer is and its seasonal behavior. And again, the same conclusions. I would like to comment and underline that the roof of permafrost can deposit atmospheric heat and cold and the excess of liquid precipitation. If we observe air temperatures, this year it can be very hot. Next year it can be cold. On the scale, a global scale, circulation processes, it's very complex. But here, it's really simple. The cold of this year is accumulated in low temperatures in permafrost and active layer. And it works as a refrigerator for the following year. The same as with the excess of liquid precipitation, which are accumulated and conserved in these seasonal ices. Thank you very much. Unfortunately, we ran out of time, although it's a very exciting presentation. So the next one is Alexander Fedorov, Deputy Director of Melnikov Permafrost Institute, Cryogenic Processes as Indicator of Global Climate Changes, case study of Yakutia. You mentioned humidity, heat regime now, and Alexander will continue that. Thank you.
Так, коллеги, презентацию. Федоров.
Так, я всех вас, особенно кто
I would
онлайн,
like to greet all of you, especially those who are online, and I'm presenting my presentation. So the topic is cryogenic processes and global climate change, and this topic is one of the
проблемных
priority topics in the Permafrost Institute.
научном плане. Здесь я хотел бы начать
Here, I would like to start my presentation with this table, and this is the chronology of development of permafrost landscapes during Holocene and Upper Pleistocene
центральной Якутии.
in central Yakutia.
Желтыми
The yellow
обозначены
highlighting
это
shows
холодные периоды.
cold periods, and between them there are warm periods.
Если говорить
And if we talk about global warming,
вот,
then usually people think that
последние вот эти
warming,
природные вот эти изменения,
that
вот это
the
приносят они глобальные
recent changes,
такие потепления.
natural changes are the result of global warming, but even more significant warming has been present previously as well. For example, the Atlantic period, the Preboreal period 10,000 years ago, and so on. And these periods have been much warmer than the present day. And during these periods, the alasses in Yakutia and different thermal karst formations have formed. And we all know how the alasses form. It's the degradation of permafrost. And these natural collapses and all the catastrophic events have been much greater in magnitude than today. And in this table to the right, you can see the characteristics of this. I would also like to draw your attention to the fact that we have a number of forecast models of how permafrost will develop in the future, and our problem will depend on this, the problem of studying cryogenic processes.
Опоздал немножко, и Владимир
Well, maybe Vladimir Romanovsky showed this forecast model.
но все равно это его команда сделала.
This has been done by his team,
Красноватый цвет
and the pinkish color
сверху это 2050
is
год,
2000, the year 2050, and below is 2100 year. This is the change, the thawing of the upper part of permafrost. And please see Yegarka on the bottom
и, короче, вот это
map, Yakutsk, Magadan, Yegarka, we are going to have significant changes in permafrost with the development of
мощных катастрофических криогенных процессов.
huge and catastrophic cryogenic processes with the melting of underground ice.
Далее, что
As,
сегодня,
what-
сегодня что мы имеем?
as for today, what do we have today? Today we have this Batagay mega slump, Yamal
Термообразие берегов
slums,
и техногенные проблемы.
erosion of course, and many different technogenic issues. These are all cryogenic processes which are connected somewhat
Глобальным.
with global warming.
Почему же мы всерьез
Why
говорим
are
о
we talking seriously about catastrophic changes in permafrost and permafrost landscapes?
часть
Part of permafrost soils contains lots of ice. These are the Yidoma complexes. And as you can see, over 50%, 60 to 80% of soils are clear underground ice. Of course, when the climate changes and warms, this ice starts to melt. And this is a known problem. The thawing layer increases due to proliferation of warmth into soil, and the upper part of ice starts to melt, and this perennial thawing of underground ice forms, which leads to the formation of thermokarst landscapes. And this is one of the most serious risks of cryogenic processes. What is the area taken by such ice soils? Up to 25 to 50% of Yakutia, and they are the most dangerous permafrost landscapes, which can, if the climate grows too warm and human activities start to affect them, they can start to melt and degrade. Here I show you in central Yakutia, this is the former field which was used until 1990. So this land was used for growing crops, but at the top you can see how the areas changed from 1990 to 2015. In 1990, in Yakutia, there have been about 100,000 square over 100,000 hectares of cultivated areas, but now we only have about 40,000. This is a drop of about 2.5 times. And the reason for this, well, nobody was trying to find out the reason for this, but we can estimate that this is due to the degradation of permafrost. And this has led to the abandonment of these areas. And such landscapes, such areas in central Yakutia, especially in Tata and Churapche Uluses, these fields, up to 50% of them are such lands. They will never recover, and they are not usable anymore. And at the bottom you see a map on which sites such kind of fields are present. They are colored in red on the map. We at the Institute are monitoring these processes for quite some time. And on the right of the slide, you can see graphs of the dynamics of destruction of soils during by thermokarsts and the average temps, the average speed of their degradation. It's up to 10 to 14 centimeters a year each year. Well, there are areas where there's a degradation of up to 1 meter. And these cryogenic processes, the thermokarst, has a significant impact on our landscapes. Here you can see a former runway of Churapche airport, and of course the airplanes will never land here again. We have always thought that anthropogenic events were the main cause of thermokarst processes, but here you can see the impact of cotton worms, silkworms. And when the silkworms come here, the forest dies out, and then this leads to the appearance of thermokarst reliefs, landscapes, and you can see it on this map. And when these thermokarst landscapes start to appear, they start to grow, and then they can merge and start affecting everything else. And this is one of our polygons where we study these thermokarst landscapes. At the top are the photos from space, and at the bottom are local photos of how landscapes change due to these processes. But we cannot say that this only happens in central Yakutia or in some select areas. No, this happens everywhere in Yakutia. The right picture here is near Temp Meteor Station on Kotelny Island, photo taken from space. And there are changes near Verkhayansk, Chakurdakh, Batagay, Selan, and so on. If we talk about the degradation of plant cover, then in this means that as soon as the plant cover is disrupted, then thermokarst starts developing. And this is our procedure. We study how much ice is melting, how much time it takes to do that. And for studying these processes, of course, we need forecasting to try and see how much the changes will be in tundra, tundra forest, middle taiga, and so on. And we make such maps. And we have created ice content of permafrost map for the whole of Yakutia, and they will be the basis for our continued work on monitoring cryogenic processes. So thank you for your attention. Thank you, Alexander. Dear colleagues, our next speaker by Varlamov Stepan, leading researcher of Permafrost Institute Melnikov, monitoring of the heat state of soils in central Yakutia in natural and disrupted states.
Коллеги, презентацию Варламов.
So my colleagues Varlamov, Skryabin, and Skechkov, it's our joint work. We've summarized 30-40 years of data collection and monitoring of thermal state of grounds in Yakutia. We published a monograph, so my report is based on this monograph. Monitoring of thermal regime of the ground started in 1981 by our institute and is conducted on the left and the right banks of Lena River around the city of Yakutsk. We concentrate our works at Yakutsk, Chabuda stations, also at test sites near the Lena motorway, near the Tamot-Yakutsk railway, water pipeline, Nizhny Bistях, Mundulach, and Mastach gas mine. So the network of monitoring was organized based on the on 7 types of physical geographical regions, and the monitoring embraced about 200 holes in 9 types of localities and landscapes. We monitor lithogenic foundations of undisturbed and disturbed landscapes, and including natural technological combined system like infrastructure systems, where we have some infrastructural facilities. So this is the scheme of the region where we do our research. We have here stations, test sites, infrastructure facilities. These are the types of landscapes. Of course, these are undisturbed landscapes such as large ecosystems, meadow ecosystems, etc. Anthropogenic landscapes are burned forests, cut forests, and other disturbed locations such as near roads and high voltage lines, and the initial stages of thermokarst near the water pipeline. These are some linear structures like railway, and what landscapes we have around. We counted how the thermal condition of upper horizons of cryolithozone, how they react to modern climate change. And there can be the following conclusions. Despite warming of modern climates compared to other regions of Russia, the change of temperature regime in natural landscapes is very weak. There are no big changes there. So the main factors that regulate these temperatures are snow and biomass, in fact. And on open meadow landscapes, the trend of growing mean annual temperature of grounds is 2 times higher than in forest complexes. And the depth of heat penetration during modern climate's warming in meadow sites made only 40-50 meters, and the temperatures of grounds beyond 60 meters is stationary. It's quite stable. The depth of seasonal thawing of grounds in natural landscapes is quite sustainable and characterized by low interannual variability. It weakly reacts to climate warming. The trend of the lithogenic foundations of natural complexes in the region in the conditions of modern climate warming belongs mainly to the category of high thermally sustainable frozen grounds. The long-term experiments in natural complexes that experience anthropogenic impacts gave the following conclusions. When you remove the insulating soil cover in lowlands, it influences the mean annual temperatures at the 10-meter depth within 0.3, 1.7 degrees Celsius. And the cutting of forests in inter-alaz types of landscapes increase the temperature by 0.2, 0.8 degrees Celsius, and the cutting of forests after forest fires also leads to increase of the temperature. And the thickness of active layer also increases. the change of intensity of the temperature by 0.2, 2.0 degrees, and increased thickness of active layer is observed in the first or stressed stage of development of forest phytocyanosis. It's within first 5 years. And then when the vegetation returns, it brings the temperature down and also decreases the thickness of seasonally thawing layer. And the most influence comes from cutting of forests and removal of suprasoil cover. And in very icy locations, disturbances lead to some dangerous cryogenic processes. And my colleagues mentioned it. The behavior of thermal status of grounds at anthropogenic impact speaks of their relative stability in sands and in unstable inter-alas landscapes when there are underground ice complexes near. The results of the research of natural technical systems or systems with infrastructure facilities. The upper border of permafrost under the motorways at all test sites is deepening, which is not acceptable for operation of roads. And the sand dikes for the roads refrigerate the underlying grounds, and at very humid and low temperature conditions, they warm it up on the contrary. We have monitored the reconstruction of the federal motorway Lena, where they made the dike higher, and the condition there is more stable currently. But still, at some sections, there is degradation of the road surface. And the territories adjacent to railways, we have more accumulation of snow cover. And also the lighting regime is disturbed, and the heat exchange between the surface and atmosphere is also disturbed. We also found out that the roof of permafrost is going up, and the ground is becoming colder under high road banks. That's it. Thank you, Stepan. I have one question. You mentioned that what is 6 meters stable status, but what is below the 6 meters in central Yakutia? So is it a stationary regime at 6 meters? No, 60. Sorry, it was not 6, but 60 meters. Below 60 meters, the conditions are stable in central Yakutia. Dear colleagues, the next presentation will be by Zin Huazun, the professor, Institute of Cold Regions, Science and Engineering, Northeast Forestry University.
Good day.
Good day.
Please, your report.
Thank you very much, President Zalezniak. Can you hear me? Can you hear me?
Да, да, мы вас хорошо слышим.
Yes, we can hear you very well.
I'm honored to be invited to attend this Russian meeting on the Arctic permafrost study. It has been a long time since the last time we visited Yakutsk in 2019. And I will give a presentation. Can you see the presentation?
Коллеги, презентацию мы не видим пока. No.
Can you see the PPT?
Ну, он просит, говорит, мы не видим презентацию, нужно ответить. No, no, your presentation.
Okay.
Я понял. Так, давайте включим. Ну, включите сами.
You can turn it on yourself. Yes, we can see it now.
Oh, great. So my presentation today will be on Tibet Arctic permafrost transect in Eastern Asia. And this will be a presentation of our colleagues and friends from Alaska and Yakutsk, including Professor Vladimir Manovsky, Sergei Marchenko, Mikhail Zalezhnyk, and Valery Inspector, and of course, Alexander Fedorov, and many other friends from MPI, the Russian Academy of Sciences. Since last time, I and Professor Zhou Zhang also transferred to Northeast Forest University in Harbin, China. As we can see from this map, we would like to build a transect, a permafrost study from Himalaya in the south all the way to Saskilach and Uninkaya in northwest Yakutia. This work, of course, first will be focused on the fire-induced permafrost degradation in Alaska, northern part of northeast China and eastern Siberia. I think now we would be more also interested in hydrothermodynamics, hydrological and ecological impacts, and many other rapidly degrading permafrost on this transect. The final goal will be on the fire-induced and other process-induced frost geohazard and their mitigations. Of course, this transect was inspired by Professor Zaleshnyk's original transect design from Novosibirsk Island all the way to India. Of course, these alternatives also include some other part which is not very well visible in this show up. Recently, we have built a new station in Jagdachi in northern Dashanli Mountains by the State Key Laboratory of Freedom Soil Engineering, Northwest Institute of Engineering, Environment and Resources, Chinese Academy of Sciences. They also have built a new station on permafrost engineering and environment in Erguna by the Northeast Forest University Ministry of Education, China. Our rationale is, of course, on the degrading permafrost, because the permafrost have been degrading ever since a long time ago, such as the last glacial maximum. And maybe the permafrost in China is degrading faster and earlier than in the Russian part. So the degradation of permafrost has profound impacts in the Arctic, in the circum Arctic region, and of course in boreal regions. Thus, we need to accurately predict, evaluate, and mitigate, adapt to the change the hydrothermal dynamics of the changing permafrost, and impacts remains the great challenges for many engineering and environmental programs. In the end, we need to predict the change with models on permafrost dynamics. But in order to use the model has to be very well validated by very reliable long-term archives of ground temperatures. So our key questions has been already mentioned by many of our Russian colleagues before. Our focus will be on how to accurately predict permafrost change and its impacts. Of course, the focus will be on the Yakutia outer Baikal regions and Northeast China, of course, also Alaska during the 21st century. Professor Fyodorov already pointed out we are very interested in the permafrost regimes by 2040 to 2050, as well as the end of 21st century. The second focus will be on the Southern Arctic and Boreal regions, and now we also have a lot of programs going on the pan-third pole, which is centered around the Qinghai-Tibet Plateau region. Among all these programs, we also have the tripolar regions comparison program headed by Professor Tingjun Zhang. In the end, this transect, of course, many other our friends are working on the longer time permafrost in the past, and also in comparison with present the future projections. So our ultimate goal will be on how to properly evaluate and prudently manage the impacts of degrading permafrost. This is the prediction by our colleagues on the present permafrost distribution, and also what could happen on the 2100 years. You can see there will be a lot of permafrost loss or thawing by 2100. This map has already been shown by Fyodorov. We can see in Eastern Asia and also in the entire Asia, there are a lot of places permafrost might be thawing very fast, especially in the southern part of the permafrost body of the Eurasia continent. Of course, some other areas also have been warming up, but their impacts will also be very significant. So the impacts of degrading permafrost, we already know a lot, still need to know more, is on the dual impacts of climate warming and human activities. We all know that in the southern part of permafrost zones, we have more and intensive human activities, such as engineering, urbanization, other cultivation programs. So we are concerned first on the environmental impacts, such as ecological systems and also the hydrological systems. The other part will be on the societal and engineering impacts on the human dimension. Of course, the last two sides also work together. This is a picture then presented by Professor Feller. This will show very intensive, the rapid degradation of permafrost could also happen in very cold permafrost, such as Yedoma area in central Yakutia. This was a very nice picture on what could happen on the Siberian larch forest succession if under climate warming or jointly worked out with the fire impacts. We can see there are some certain kind of the life cycle of fire or disturbed permafrost and the boreal ecosystem work together. So this is a very complicated process. Another big concern from a global dimension, or particularly in the carbon program in China now, is on the permafrost carbon emissions. We all know that permafrost contains a huge amount of organic carbon, and for the carbon neutralization program, we have a long way to go, and it's a very urgent program to be deployed. In our School of Civil Engineering, we of course are very interested in the geohazard and their mitigations in both Yakutia and in China. Peter just shown this very nice picture, show very well about the human and natural interactions, jointly worked out such kind of landscape in Yakutia. Of course, my first job upon my return from Alaska is working on the Russian part, such China-Russian crude oil pipeline system, which is the spur line of the Eastern Siberia to Pacific oil pipeline system. This pipeline has been in operation for more than 10 years, and it works reasonably, but it still have a lot of geohazard to be mitigated, such as the ground surface subsidence and some part of the exposure of the pipelines. We already know there are a lot of, maybe hundreds of meteorological, hydrological, and weather stations, and also permafrost stations used to be built in Soviet time and also working in Russian educational and other ministry departments. They're all very nice. We would hope to work together with all these stations and probably try to help to either doing the observation there or help to reopen some of the now already halted stations there. Since the year 2017, we have made several visits to northern Yakutia, including to go to the Anabar Basin and Saskatchewan in 2019, and also a visit from Yakutsk all the way to Tinda. Some of our friends also visited Moscow and other places. So these are all arranged very nicely by Professor Mikhail Zalezhnyak, and many of our friends are very appreciative of these efforts, and we are looking forward to working with our friends. Of course, the first very successful establishment was the Asia Cold Regions Engineering and Environment Research Center, jointly on 3rd of April 2017 by Professor Zalezhnyak and also Professor academician Lebedev. We have a lot of academic exchanges along the trip, and also discussions with many of our scientists, the leaders, and also the governmental officials. We have more than 15 people times visit Yakutsk and Moscow, and also about 10 people times to come to Lanzhou, Harbin for visit. We also have jointly educated some of the students and hosted some postdoc in Lanzhou and Yakutsk. In some of the program, we also have done some research on the permafrost and geohazard along the prospective Beijing to Moscow engineering corridor, including the distribution and their features, permafrost and the frost hazard along the engineering corridor. Some of the consulting reports have also been compiled by joint efforts of Russian colleagues and the Chinese friends. Professor
I'm sorry,
I'm finishing,
but 1 minute we have.
Okay, great. So we work together also with Spectre, and the paper was published in the Russian journal. So we have a lot of inadequacies, and it's already pointed out by Zalezhnyak. I will not repeat. So for perspective, we have a lot of work already built in Russia, and some others are being on the perspective. So we have a great future to work together on these monitoring systems, especially on the fire impacts. And this has already been mentioned by Professor Zalezhnyak before, so I just want to emphasize that we need to educate a lot of students and provide opportunity for them to grow. So I would like to emphasize that not only we need to understand the present permafrost, we also need to rebuild the history of paleopermafrost across the Asia continent and also in different transects. So this, we are proposing some new programs and the joint study of Russia and China, and of course, maybe also Alaskans. So thank you very much.
Zin, thank you very much. Thank you very much, your report.
Thank you. Thank you, Mihai.
Уважаемые коллеги, следующий доклад.
Dear colleagues, the next report by Zhang Zhongqing, Associate Professor, State Key Laboratory of Frozen Soil Engineering, Northwest Institute of Eco-Environment and Resources.
Изменение вечной мерзлоты на северо-востоке Китая.
The changes of permafrost in northeast China. Do we have Professor Zhang?
You hear me?
Yes,
Yes, okay.
Yes.
Yes, we can hear you.
Yeah, good. Hello, everyone. I'm glad to share my topic with you. My name is Zhongqing Zhang from State Key Library of Frozen Soil Engineering. Today, my topic is the permafrost change in the northeast China. Our work will be introduction through the following aspects. Thin and Baker permafrost is the transitional types between the Hess latitude and Hess altitude permafrost. Permafrost in the northeast China is located and the south end of Thin Baker permafrost. And the permafrost in the North China is one of the most significant change areas in the world. Permafrost in the northeast China with its mean annual ground temperature thickness sensitive to the climate change. Permafrost is degrading active lining thinning, mean annual ground temperature rise, and so on. The main annual air temperature increase rate in the northeast China is significantly higher than that in the North Hemisphere. And the Xinjiang Baikal permafrost region in the past 13 years, it is the fastest state of climate change. As the climate change, how does the change of permafrost in the North China and what facts affected it? In order to investigate this issue, we carried a series of model calculation. Object law of permafrost change discuss the influence of snow precipitation on the permafrost change. Data such as weather station data, survey data, renaissance data, and so on to be viewed in the calculation. We use this data to complete the data calculation, model verification, and data analysis. First, the model calculation results are compared with the service data, and now the basis to the north temperature data condition first the numbers and the TTOP models could describe the change of permafrost. The area of permafrost varied between the 36,000 and 47,000 kilometers. The permafrost is distributed north of the 36 north latitude, generally decreted, and the south boundary shifted to the north. Compare with the continuous and discontinuous permafrost. Specific permafrost decrease slowly. Based on the results about TTOP models, the TTOP results, the TTOP are greater than the -6 thresholds in the moisture area. TTOP temperature in the moisture area decreased by 1.2 to 2.6 Celsius. Compare with now after the 1990s, the decrease rate has slowed down. The permafrost decreases influenced by many factors. As see the pictures, we can see the main annual air temperature increase is the main cause of the permafrost degradation. But since the 1980s, the influence of air temperatures has been weakening. And the snow shows the insolutions and the warming effect. The snowfall warms the ground surface temperatures of 1.1 to 10.2 Celsius in the cold season. Meanwhile, the rainfalls cooling the surface temperature in the wet season. But in the year, the rainfall warming the ground surface temperature. In the area, the snow and the rain's influence on the ground temperatures have some change. The influence of snow covers weaken from west to the east, and while the influence of the precipitation is opposite. Finally, we get those four results. Permafrost is generally degraded in the northeast China, and the continued and discontinued permafrost are degrading faster than the sporadic permafrost degradation has slowed down since the 1995. Main annual air temperature increase is the main reason for the permafrost degradation in northeast China, and the influence of temperature has weakened in the recent years. Regionally, environmental factors such as snow and precipitation all affected the permafrost degradation, and the warming effect of snow cover is more than the rainfall. In the local area, the influence of snow cover weakens from west to east, while the influence of precipitation is opposite. The degradations of permafrost in the northeast China as the result of combination effect of climate warming and environmental factors. Thank you for your attention.
Thank you very much. Так, уважаемые коллеги,
Dear colleagues, if we have questions, we can ask them now, because our presenter has extra 2-3 minutes. No questions. Then we go to the next presenter, who is Iosif Makarov. The company called Geolan, digitalization of monitoring of Cryolithozone in the Russian Arctic. We can hear you. Hello, once again, dear participants, and today I would like to talk about the digitalization of geomonitoring in the Russian Arctic. This diagram shows the temperature regime. Everyone knows it, but not everyone has thought how the database is built. The database containing all the data by year, temperature data. Today, there are some problems. We don't have a unified online system. All the data are kept separately. And there are over 4,000 files that comprise the database. And annually, about 5 to 10% of data is lost. And the experts can't find the information in time, and they spend 60 to 80% of the time to search for that information. The measurements in the field, on the left you can see the thermal string that is buried in the hole. It requires drilling and data sensing, and it is all done manually. And the data accumulated by the logging equipment and is transmitted through radio. It's only up to 100 meters radius. In Russian Federation, we have a draft of law, a federal law, according to which Roshydromet will be the operator of accumulation of this data. They will set up this network of stations, and this concept will not embrace, first of all, residential areas that we mentioned today, because permafrost is melting under houses, which is crucial for people. Then the other things not included into this network, it's business communications, roads, other transportation routes. We suggest to use up-to-date technologies of transmitting this data. It's Geo1, LoRaWAN, and these are open source frequency ranges where we can transmit data up to 10 kilometers, to the distances of up to 10 kilometers. So the thermal sensing sensors will be in the ground, and it doesn't matter what length it is. And above, on the surface, we will have a transmitter, and it will be transmitting this data online to the LoRaWAN base station. And right now, the process is already automated, but collection of data is done by people. They go there and then they take the data. So the scientists, in order to collect all the data, they have to travel to each thermal sensing string. Then they have to hook up their device to that thermal string, and then they collect the data. This mode of work is currently becoming outdated. I think we have to develop further and start using more state-of-the-art technologies. Today, we have developed an industrial sample, and we are creating a geoinformational system. At the start of the Northern Forum, the head of the Republic mentioned that we are starting to create this geoinformation system. And I would like to underline that when we create this resource, the stakeholders are not only just state, but business community and academia. So our suggestion is to use this open source data so that the state and the business and academia could have access to this data and could be able to have these tools to process and analyze the data accumulated. And after that, there will be no problem in collecting the data. It will be done automatically. We will no more have the problem of storing and analyzing the data, because we have lots of free tools for processing and analyzing data, like Pandas, like Orange. They are all free, where we can also use it for forecasting and modeling. We are open as an integrator. We can use the best solutions available on markets. I won't name the exact companies. We think that it doesn't matter who is the manufacturer of the equipment. The most important thing is to provide the state, science, and society and business with very relevant data on the condition of permafrost. So for the state, this cooperation will be very good because the data will be collected at these Roshydromet stations, and all this data will be accumulated not only from this network, but also from businesses and from science. And there will be more substantiation for the research and for forecasting what might happen here. And for the science, the advantage will be that today we have a lot of free tools. We can share them with the academia to help them in their work. And we position ourselves as a business structure who will be commercially providing services of monitoring for residential facilities, road facilities, etc. Plus, we will have some scientific support. And the society, communities will have access to this information, substantiated, very reliable information, because it will be accumulated automatically. So this was my idea, dear colleagues. We are launching one pilot site in Yakutsk. It will be automatically collecting data and transmitting it.
Хотелось бы сказать, что
in Yakutsk, we already installed some thermal sensing strings, and along with building our information system, we are now developing a universal controller that will be attachable to all those thermal sensing strings that are already in the ground. At the same time, we have some questions. Maybe we'll discuss them during Q&A, or maybe you, Mr. Zhelezniak, will advise us. So who is the owner of such equipment? For example, when they build residential high-rises, we have this permafrost controlling agencies, and the developer should install this thermal sensing string, right? But who is collecting the data from those strings? Maybe you, dear colleagues, know who we should contact to organize the collection of such data. So that's it from me. Thank you. Thank you, Iosif. We still have 2 questions. Maybe we have some other questions because we have 2 minutes. No? Okay. I have a question. Such systems of monitoring, have you already installed any? Have you already started using some? And do you already have some data sets? Have you tried analyzing it? For now, we don't have anything ready. Right now, it's still in the installation stage and adjustment stage. We're trying to find the best controllers with which we're going to work in future. Both thermal strings, we are looking for big vendors. We found 4 of them. We found out that each of them have their own software. That's why it's still a project to be implemented, but we have some model equipment to show. Thank you. Dear colleagues, we go further, and the next presenter is Go Ivahana, Professor, International Arctic Research Center, University of Alaska. Please.
Да? Так, значит, слово Го Ивахана, профессор Международного центра арктических исследований Университета Аляски. Пожалуйста, презентация.
Center University of Alaska, Go Ivahana, please. Thank you, dear moderator.
Добрый день.
Hello, everyone. Today, I will be talking about the method of microwave remote sensing that measures thermokarst deformation from space. So this map shows the distribution of Yedoma complexes that consists by 70% from ice in the deposits. Yedoma exists at large scale in Siberia and in Arctic America. In central Yakutia, we also have Yedoma zones, just like in Fairbanks, where I came from. As a result of thawing of underground ice, we observe subsidence of surface. We know this event as thermokarst. On this slide, you can see an example in the village of Silan near Chorapcha. We want to know how fast the permafrost will thaw and the ground ice will disappear. We want to know the rate. I will show you how modern remote equipment can monitor thermokarst processes from space. And the goal of this study was to conduct case studies of field service and remote sensing analysis. So we want to confirm the results of remote sensing by field service. In such way, we can provide spatial and temporal information on thermokarst for the locals and for the leaders of community. So this method is called INSAR, Interferometric Synthetic Aperture Radar. The satellite emits electromagnetic wave on the surface of the Earth and receives the reflection of this wave. And at the next measurement, the satellite can record the difference between electromagnetic waves. It means that the height changed between the first and the second measurement. So to be simple, this method measures the difference of distance between the satellite and the surface of the ground. Let's look at the case study. It's in the field near Maya village. Here you can see the vicinities of Maya village, where we have forests, alasas, arable lands, and other open sites. So this INSAR method shows the stable parts of this field in green, and the blue color here shows subsidence up to 4 centimeters per year. For this analysis, we used ELOS pictures of JAXA. If we compare it with the optical photos, we see that at the open places we have more subsidence. So we can compare these two, especially in abandoned arable lands. When we look at the other period, we see another spatial pattern. Some part is stabilizing, but the other one is starting to subside. So the field studies confirmed these subsidence processes in the open areas. This is locality near Batagay, where we have a world-famous place which is called Batagay crater. In 2004, in 2018 and 19, near Batagay and near the Batagayka crater, there were very big wildfires. We chose this place for our study because there might be some very sharp thermokarst processes, very dramatic thermokarst processes after wildfires. So in the areas affected by fires, burnt areas, we had temporal subsidences. But outside the fire zone, the ground stayed stable. And subsidence occurred only inside the burnt area, as you can see in the yellow color. The most intensive subsidence occurred at the first and the second year after the wildfire. After that, we recorded a gradual evening out, relief of this subsidence. Again, here are the pictures from the field. In the burnt areas, thaw depth is 3 times bigger, deeper than in unburnt areas of the forest. And the last example is the city of Fairbanks, where I live and work. We also have Yedoma there. These red areas show the subsidence processes from 5 to 10 centimeters per year. These red dots coincide with the areas of arable lands, roads, and even golf courses. So this INSAR method can be used to detect spatial variation of permafrost landscape. And our data shows that we can measure it with quite a high accuracy, the quantitative parameters of subsidence. But we still lack some field data to confirm. There is no doubt there is a demand for such analysis, and it's becoming more and more relevant in northern regions. Thank you for your attention. Thank you, Go. Dear colleagues, we have a few minutes for questions. I have a question. So the accuracy of measurements, what is the accuracy of measuring subsidence? The accuracy, at every place they're different rate of accuracy, but I can show you the dimension, millimeters or centimeters. It always relative. Sometimes it's stable, sometimes it's changing. So it depends on conditions. Stable, you mean that these errors can be up to 1 centimeter? Yes. Any other questions? How the status of humidity affects the condition of surface? How does it influence the reflection? There is an error due to humidity of surface, yes, and then there is impact of vegetation. But it depends on the length of your wave. The longer the wave, there will be less influence because magnetic waves penetrate vegetation. There were several cases when we recorded errors due to humidity and water, but it was less than 1 centimeter. Thank you. Thank you. Dear colleagues, We finished the reports about monitoring, except for one report, a very exciting one, which we postponed for tomorrow at 9 or 10 at the following section. So hopefully we will be able to listen to that report tomorrow, because Vladimir has a vast experience of monitoring, and it would be a pity if we didn't. So we looked into and discussed monitoring systems and asked questions: what should we understand as monitoring? Both guidelines, methods, methodology. But I think we all agree that the system of controlling the processes, the thermal regime, underground water, humidity, water content, we should have regional systems at regional level, and there will be such systems all around the world, I believe, in order to substantiate our forecasts. Because the data that was presented today shows that the results, the reaction of permafrost to climate change is different, and it depends on a lot of factors. So I would like to thank all of you who participated in this roundtable. I am sure that we have all the contacts of each other, and we will be ready to cooperate. So we shared our results for future cooperation. We've heard many interesting ideas from our Chinese colleagues on some joint projects, and I hope this roundtable on monitoring systems, it was very fruitful and practical. Thank you. We will have a 5-10 minutes break, and we'll continue our section. Thank you. Okay, 10 minutes. And 20 minutes to 1 p.m. we'll start Yakutsk time. So we will start at 12:40 Yakutsk time.
Так, уважаемые коллеги, еще раз добрый день. Мы с вами продолжаем заседание.
Dear colleagues, we are continuing our roundtable, and this is our second section about the stability of engineering equipment in the Arctic. And we need to listen to 3 reports, and the following reports are going to be tomorrow at 9 in the morning Yakutsk time. So, dear colleagues, I would like to give the floor to Andrei Jung, PhD, research scientist at Melnikov Permafrost Institute.
Да, все хорошо.
Пожалуйста.
Слышу. Вы меня слышите?
Да, мы вас слышим хорошо, пожалуйста.
Здравствуйте, уважаемые участники.
Good afternoon, dear participants of this roundtable, and I would like to talk about the road construction using heat isolating materials in cryolithozone. At the moment, the total length of roads and railroads in Russia is about 100,000 kilometers. So in most of these regions, they are industrial regions, which constitute up to 11% of the GDP of the whole country. That is why the reliability of road network is very topical for us. We are actively using modern materials in order to increase the reliability of roads. When building roads in permafrost grounds, this is necessary in order to prevent their thawing. And at the moment, we are using extruded pentopolysterol, which has low heat transfer rate, hydrophobic qualities, and low mass. And the most recent method of using these materials is the one proposed by HPIS. And it is about laying the heat isolator on a slope, and this leads to the decreasing of thawing and basically cools the ground underneath. As it is known, the slope does actually influence a lot the heat exchange between the ground and the air. And these slopes, they reduce the qualities of the road cover and increasing the reliability and safety of these roads. Lower layers, they have a cooling effect, while the higher ones, they have a warming effect. And this technology that we use, it leads to heat isolation and reduces the thawing layer of permafrost. This is the energy balance of the heat cover, and we can say that the permafrost cannot be basically safely left there if the thawing layer becomes lower than 1, the index of 1, and this leads to the refreezing of the permafrost underground during winter. And this is our task, to reach the level of the energy balance of less than 1, of more than 1, in order to prevent the thawing of permafrost.
На этом слайде показан энергетический баланс поверхности откоса в зависимости от
balance of the road cover depending on the value of the M parameter. And if there is no heat isolation, then the value of M is less than 1. That is why our road cover and permafrost is basically thawing. So the efficiency of this method has been studied at the Yakutsk highway at an area of about 100 meters. And this is a road with a height of about 4.5 meters. And there are a number of properties that make it ideal for us, including the width of the road of about 70 meters. And the permafrost layer here is about 200 meters. And its temperature changes from 2 to 2.2 degrees centigrade, negative degrees. And the properties of this permafrost in this area is its saturation with ice wedges. And there are soils there are thickness of about like 25 to 30%, and their depth is up to 10 meters. In order to evaluate the efficiency of this method, we used a computer, and we used the data from the meteorological station of Yakutsk, and we have also did some boring work in order to evaluate the thermometrical research. And in order to do this, we used the georadiolocation method. We used georadars with frequency of 100 and 400 megahertz. And this allowed us to detect the layers of the permafrost and thawing layers. And this has allowed us to see that the thawing layer, the upper layer of permafrost, is at 1 to 2 meters below ground. And here you can see the location of the permafrost when we started the research. It's number 2 here. And then the beginning of the permanent layer of permafrost in 2009, the 3 here. And number 4 is the results of pneumatic modeling that shows the upper layer of thawing grounds. And 1 is the mathematical models of results if we didn't have heat isolation there. And we can see that in order to see the efficiency of this method, we can compare the lines 3 and 1. And the analytical calculations that we have used led to these following results. And this shows the depth of heat isolation that needs to be used in different regions of Yakutia in order to prevent the thawing of permafrost. This mostly in central and western Yakutia, where there is not much precipitation, but in other places where there is higher precipitation, as you can see in this slide, the analytical calculation showed that this method can be used. Basically, all our results led to the conclusion that this method can be used everywhere where there is permafrost. And we have compared the method, our method, with other possible methods. And all the calculations have been done in different regions, areas of the road. And the calculations have been done using without taking into account the transportation costs and other costs. And this has shown that our method is it's actually the least expensive ones and one of the more effective ones. And these are our conclusions that we have reached. And this new experimental method, it allows to isolate permafrost, and it allows it to basically remain at an equilibrium and prevents it from thawing. And this has been done on the results of our research that has been going on for about 4 years. And at present, our method is basically ready for application, and this is a good thing. Thank you for your attention. Thank you very much, Andrei. If you have any questions, please. Yes. About the longevity of this cover, are there any facts? Well, the main enemy of this material is solar radiation, but because most of the time this material is underground, as the producers say, as well as some of the previous research shows, that it all shows that this material is actually has quite a lot of longevity. So had there been any experimental works on this pentapolysterol? Did they show how long can it last? Well, there's some data on Viluy highway, and its isolator has been there for like about 10 years or more than 10 years. And very recently, I think last year, we wanted to try and see what happened to this insulator. But it has not been done yet, and our institute is also planning works to study the impact of heat insulating materials, and it will be done on the basis of the road faculty of Northeastern Federal University. So we don't have the data yet, and we will talk about that later when we have the specific data. So what is it like? Can this material be okay for 10 years or 20 years or something? And Viluy, you mean the highway? Yes, Viluy is the road, the highway that we have. But I personally estimate that this material can last for over 10 years. Because in the IAM highway, where this material has been laid at a depth of about like only 10 centimeters or so, the results are quite good. So how long has it been there? Well, over almost 8 years there. And it's still in good condition. Thank you. Dear colleagues, any more questions? Okay, then, thank you. Andrei? Dear colleagues, and our next speaker is Fyodor Poselsky, head of the Department of Industrial and Civil Engineering at Northeastern Federal University.
It's the safety of residential buildings. Thank you. My topic is buildings and structures, and my report will be about the problems that we have to keep in mind, especially during the climate warming. Yakutia, due to its climate, it's kind of an experimental site for construction in extreme conditions. The requirements for frost resistance for foundations only were drafted in 1970s, 50 years after such buildings were started to be constructed. So there were over 20 failures of such buildings. And of course, during climate change, these problems might present a risk, and we have to take some preventive measures to reduce those risks. And here, the presentation is about the mass typical prefabricated buildings. There are about 5-6 types. One of them is called the Khrushchev era houses. This is not very high buildings, 4 to 5 stories, brick blocks or large blocks. They were started to be built in 60s. And it's bad that they have a low and ventilated space under the building. Here are some key aspects mentioned, and the red ones are the drawbacks affecting their safety. So the space below the first floor is very small. Yesterday, there was this news on the internet that one of those buildings was severely damaged, and the bricks just were destroyed because they were not appropriate for our temperatures, and these houses are quite old. We can see that there is a lot of fluctuations of temperatures and humidity, and those old bricks were not fit to that. Then this is the next type of houses. We all know these large prefabricated blocks. They have one drawback. They have concrete of not appropriate class. According to modern requirements, it's not appropriate for building. And then this is the next type of our buildings in Yakutsk. It's again the large prefabricated panels. By the time when they were started to be constructed, we already had some guidelines for construction on permafrost. The guidelines were developed by experts, but still we have some problems. At the ground floor, we have some structural problems. And the main thing is again that this below the first floor space is very low, and the infrastructures are leaking. So there is a lot of destructive impacts, like corrosion of reinforcement bars, etc. These buildings are not compliant with some other requirements as well, like insulation and fire safety. Then the next type, a later design from late 80s. They are better, but still they have one drawback. These two side walls are made of the type of concrete that are prone to deformation. And again, the structural stability is also not sufficient. Another problem point are the buildings and blocks of buildings built on artificial sands. Latest research show that the expected freezing of grounds below these artificial banks, it did not happen. In fact, all of them are in thawed condition. And probably they will be even more dangerous in seismic-wise sense. So these buildings were constructed without consideration of seismic safety. There is another district on artificial sands that was built already with the compliance of seismic safety, but still they also have some problems because there is a lack of information of the ground conditions under those buildings. We recommend not to mix the first and the second type of the grounds. Then we have new buildings starting from late 90s. They are frame-based monolithic buildings. And these buildings are quite reliable, but the weak points are that the floors are resting on columns without beams, and in usual conditions they will be quite reliable, but if there are some subsidence deformation due to ground degradation, we still don't know how will they react. And the designers of these buildings tried to save money probably, and they didn't use monolithic structures everywhere. So here you can see what I mean. In the old buildings, the monolithic gridding framework is absent, and for structural stability of the building, they are not really helping. So beamless floors are not very rigid, and all of these types of buildings should be assessed for possible susceptibility to deformation. First of all, we have to look into technical documentation, like design, operational documentation. All of the buildings on permafrost should have these documents. Of course, monitoring, etc. Regarding the technical and documentation, first one, design documentations, we don't have almost any for the older houses. We have some part of this design documents because part of the archives were destroyed. So for some houses we don't have any data. Earlier houses, we also, it's challenging to find design documentation for buildings, for some of them. So it is very hard to find any necessary information about these buildings. This is building 19 in microdistrict 202. For example, what concrete they used there? Second column, this is what was required, then what was used in fact, and then what concrete was used according to our tests. We see that the materials used did not comply with the modern regulations. Some of the parameters are okay, but some are not. This is the reinforcement data of the bearing elements, the designed one, the required one, and the real one. It's again some worrying data because they don't comply with the acting regulations. The reinforcing elements some of them do comply with requirements. So these are the examples of failures of buildings in Yakutsk. We analyzed the reasons of 18 failures, and in 14 cases it was the destruction of foundation. Deformation of buildings is not really big in Yakutsk, unlike in other Arctic cities. But here we see another. Probably these deformations and failures were not due to warming of grounds. So if there will be this warming of ground, probably we will have more problems. These are the main reasons of failures and why the low space below building is not good. We can see that the forces will act in such a way that if we take, instead of 1 meter, we take half a meter, the lateral forces will increase 8 times and the bending momentum will increase 4 times. That's why the lower understory is worse. First of all, they're not ventilated enough, but also they have some structural defects. The piles are cracking, then humidity affects it even more. And you can see it on the photos. We inspected the boiler houses of Yakutsk. The piles are decomposing. And we also observed one of the buildings in the microdistrict 202 on the artificial sands. It has an inclination, and we had to look into the reasons. So the main reason is what it was standing on silty grounds, and the thickness of this silty layer is 3 meters, and on the other side, not inclined, it's 1.3 meters. So it's a deformation due to stress of the structure. Out of 313 buildings, only 33 have functioning temperature drill holes. These are the data for load on the pile foundations. again, the disbalance in this will affect the subsidence of these pile foundations. And we suggest to create a laboratory for this research of these buildings. We have appropriate software. We've developed a software solution. So what are the conclusions? First of all, we have to come up with a republic-wide program of ensuring safety of buildings in Yakutsk. We also have to have a standing geotechnical monitoring and also inspect the buildings with low ventilated understories and develop a unified approach to designing buildings in artificial soils and probably create a center of computer modeling of comprehensive systems. Thank you. As we have thought and statistically see that we have many problems due to concrete problems and foundation problems. Dear colleagues, the next presenter is Polina Cheplyeva, ecology expert, Expert Center Project Office for Arctic Development, PORA. Can you hear us, Polina?
Да, все отлично, организаторы мне включили
Yes.
микрофон. Добрый день.
Good afternoon, and I represented the Expert Center Project Office for Arctic Development. And first of all, I would like to thank you for this opportunity to speak at this roundtable dedicated to this very important topic, because my report is slightly different from the previous ones. And today I would like to present the project which is now being designed at our office, and it is called non-permanent permafrost.
Проект называется «Не вечная мерзлота».
So it's called, and why we have decided to start this project and what is it? Well, I think it has been said a lot already, but we should repeat some things. That at present, researchers are measuring climate change, global climate change, and there is a fact that in the Arctic, these changes are speeding up, and they are more pronounced there. And there are many different models that connect the climate change and the thawing of permafrost, which is not permanent anymore. And there is in the Arctic, there's an issue of the availability of necessary specialists. The Arctic is a strategic region, and it is necessary to realize innovative projects there, and for this we need highly trained specialists which will be ready, first of all, to react rapidly to changing conditions, who will be able to make the right decisions if there are any emergencies, and who will be making right decisions in such situations. And the foundation for this project is the decree of the President of Russia that it is necessary to create a systemic monitoring of permafrost. And of course, the researchers are talking about that for quite a while now. And it is good that this is of state significance now. However, the problem is that despite there are people and organizations have been defined which should work on this, and that the researchers have different opinions on how this needs to be done in the stationary, maybe it needs to be done in stationary stations of Rosgidromet, or maybe special field areas need to be created for this. This has not been decided yet. And after analyzing all these issues, we have decided to create this educational project, which will be dedicated to the issue of permafrost degradation. And the gist of this project is to collect professional analytical reviews from researchers and technology reviews from practitioners. That is to become a bridge between the science, research, and business and state on the other side, because everything is changing so fast, and it is necessary to look at this issue from different points of view and to find some kind of a compromise solution. And we would like to do this and to become a platform where such a dialogue can be constructed. At present, we have attracted the geography faculty of Moscow State University and cryology faculty, and in this report is also an invitation for you to take part in this project in order to give us maybe some new ideas or new points of view on this issue, because this topic is very necessary at this moment, especially among the students and so on. Especially those who study permafrost and cryolithozone and so on. And we would also like to become the part of the system which will train very good professionals and specialists who in the future will be able to use their knowledge and skills in practice. So what is the portal? What kind of subdivisions does it have? Chapters. First of all, it's the monitoring, and this is talked about a lot. And here we're going to be looking at different approaches to the organizations of the system, and we're going to be talking about the step-by-step changes that are taking place in the organization of this monitoring system. And we also want to give an interactive map, which we call the emergencies in a permafrost zone, where accidents in this area will be pointed out, which are connected with permafrost degradation or maybe some wrong decisions at some points of time, in order to give an interactive visual representations of these emergencies. And another chapter of this website is analysis and events, where there are going to be analytical reviews, where we're going to be talking about new developments in the research community, about the events, about the key events that will be taking place in this sphere, and we will be presenting analytical reviews, as I said earlier. And another chapter is the experience of companies, and we would like to talk about the best practices that are being implemented at present, the practices which have proved their efficiency and their effectiveness, and which are new maybe at the moment, but have a good potential. And the other feature of this project is its educational part. We have taken up this mission to show the theoretical foundations of permafrost, to visualize the cryogenic processes, to talk about what is permafrost, what is the active layer, so that it could be very easily assimilated and learned by those young people who would like to connect their life with working in these territories. And we think that this will be very useful and effective for teaching them. And as such, we would like to make this project scientifically sound and practically applicable and very modern and interactive. So I'm not going to be showing you this video, but I would like to show you how it will look like in general.
Так. Минуту. Ладно, тогда не буду лучше задерживать, потому что все в итоге у меня подвисло из-за этого.
So it seems...
Так, сейчас.
Вы закончили, да, Полина?
Да, выключилась. В общем, я хотела показать немного видеоролика.
I just wanted to show you the video, but I did talk about that in the presentation. So I am ending my speech on this, and I would like to invite you to participate in this project as people who have a huge experience in the field and who can share many things with the general public, both with young people and with specialists and experts who are going to be developing the Arctic in the future. Thank you very much, and I hope for further cooperation. Thank you very much, Polina Dmitrievna, and we wish you success, because this kind of educational and enlightening activity is very necessary for training specialists, especially in central universities, where the students don't know that much about this. So I have a question. So permafrost, what do you associate it with? With eternity or maybe a century? So mostly, well, the paradigm has changed now. When I was studying in a university, we were sure that this is eternity, that it is something eternal. But now we understand that, of course, this is a certain stage in the history of the planet, and which is changing right now. And our task, of course, is to monitor it and to react to this. And, of course, the word permanent, permafrost, in permafrost, perma, it's from the word century. And thank you very much. And yes, I will conclude in this. That is why we're calling our project non-eternal permafrost. It's slightly ironic. Yes, there are like the terms, and there's a very good book by Igor Nekrasov. Is the permafrost permanent? Thank you very much once again. Dear colleagues, we are now concluding today's section. And we are probably not going to be making any conclusions today, because we have listened to very interesting reports connected with the use of materials for providing stability and the analysis of the state of engineering conditions under different constructions, And we have also listened to this interesting report about the Expert Center project. And tomorrow we are going to be meeting again at 9 o'clock Yakutsk time. And we have about 8-9 reports tomorrow. Thank you very much for your work today and good day.